All right, so last time we left off in the middle of section 4.2, talking about graphing rational functions. And the kind of functions that we looked at before is when the degree in the numerator was either equal to the denominator or smaller. So what that meant is you either had a problem maybe like this. That would have been like an example problem we could have tried to graph. So the degree in the numerator and denominator were the same. Or I can make the degree in the numerator smaller, just x to the first. And that also would have been one that we would have graphed. Okay. In both of those cases, you end up with horizontal asymptotes. Okay? Because if you find the EBM here, what's the highest degree term? Oh, let me just get rid of this now that I changed it. Okay. What's the highest degree term that's in the top? Jade, what's the highest degree term in the top?
3x.
What is it?
3x.
Yep, 3x. So 3x would be in the top. And how about Travis, what's the highest degree term in the bottom?
2x squared.
Yep, 2x squared. And then when you simplify, okay, all the x's in the top are going to cancel, and you're left with 3 over 2x. That's the EBM. Okay, anytime that you're left with a variable in the bottom, okay, remember that variable, when we look for a horizontal asymptote, you're letting this variable approach infinity. That means the bottom is going to get really huge, the entire fraction gets really small. And what would the fraction approach here as x gets bigger and bigger? What would happen as x gets bigger and bigger? What would that fraction get close to?
0.
Yeah, we get close to 0, right? Because if x was infinity, the bottom is infinitely large, and the top is just the number 3. So 3 divided by something infinitely large approaches 0. Now, when the degrees are the same, if we look at finding the EBM there, okay, what happens now is we have 3x squared over 2x squared, so all the x's cancel out, and you're not left with any x's. So that's your EBM this time. Okay, 3 over 2, that's a constant. So no matter how big x gets, there is no x in the EBM. So the EBM stays at 3 over 2. Still a horizontal line, but this time it's a horizontal line at 1.5 instead of before it was a horizontal line at 0. Okay. So as long as you're doing the kind of problems we talked about last time that fit this description, you won't ever have to worry about anything other than horizontal and vertical asymptotes. But today, we're going to look at the kind of problems where the degree in the numerator is bigger. Okay. When the degree in the numerator is bigger, you will no longer have a horizontal asymptote. Okay. That's going to be replaced by something else. You can still have verticals. How do we find vertical asymptotes? That's totally different. That's when, what are you looking for vertical asymptotes? Yep.
It's the root.
It's what?
The root.
The roots of the what? So it is looking for roots, but we got to be a little bit more specific. The roots of the, well, Marcelo, do you remember? Vertical asymptotes. How do we find them? Somebody must have it, I hope. Yeah? Well, it depends whatever the variable is. So you're solving for what number you could plug in that would make something 0, or in other words, the roots. But we have to be more specific because it's a rational function. It has a numerator and a denominator.
The 0 of the denominator.
The zeros of the denominator, except the only time you wouldn't get a root if the denominator is 0 is if you have a what? There is a case where you can get zeros in the denominator and they're not vertical asymptotes, yeah?
Like hole in the function.
And that occurs when you have what? Yep.
Common factor.
Common factors. Okay, good. So if you have common factors, that's kind of an exception. You can get a hole in the graph. But yes, in general, the vertical asymptotes are when the denominator is 0. So because we have a degree in the top that's now bigger than the bottom, we have a new thing. Okay, this is something we haven't talked about before. It's called an EBA, not EBI. Okay, end behavior asymptote. So the end behavior asymptote, even though it's a new term, the way you find it is something we already have done before. So it's not going to be a new process to find this. So let's say you had a polynomial. Okay, when we do an actual problem, it'll be something like this. I'll give you a numerator, and I'll give you a denominator, and the degree in the top will be bigger if I ask you to find an EBA. And so you have two polynomials. And when we divide them, okay, you'll get two things from the division. You get a quotient, and you get a remainder. Now remember how you can write something when you do long division. You can write it in what's called polynomial form. That's quotient plus remainder over the original denominator. It's exactly the same way you do long division when you want to write something as a mixed number. Quotient plus remainder over denominator. Okay, we're just calling the remainder r of x. We're calling the quotient q of x. And the original denominator was g of x. And that's exactly what I filled in my formula, just the names that I'm using instead of the words. Quotient plus remainder over original denominator. When you do that long division, the part that you want to focus on is the quotient. The quotient is the EBA. Right? So it's something we already know how to find. We're just going to call the quotient the EBA. Okay, so we're going to practice a couple sketches, and then we'll also just practice doing not a sketch first, just finding an EBA if I give you an example. So it's end behavior asymptote. Now I just said this a minute ago, but what are the two kinds of asymptotes we've been looking at so far? We either could have, yep,
Horizontal or vertical.
horizontal or vertical. Those have been the only kind of asymptotes we've looked at. Okay. So keep that in mind. Okay. So any questions on how you find the EBA? Now, when we do the division to find it, what are the two kinds of division that we've learned with polynomials? You can either do, yep, long division, or synthetic. Yep. So if synthetic applies, I would use that because it's faster. Okay. So let's look at this one. They're not asking for a sketch. Eventually, we are going to sketch this one, but we're going to lead up to that by starting by finding the EBA. Okay, so quotient, remainder, and EBA. So it's definitely a division problem. First question is, does synthetic division apply? Can we use that here? What do you think, Marcelo?
Yeah.
Yes, we can, because we are dividing by x minus a number. And Marcelo, when I do the synthetic division, what number goes on the outside?
2.
2, good. And what number goes out, or what numbers on the inside?
2, -4, 0.
Yep.
3.
And 3, perfect. 2, -4, 0, and 3. All right, so we'll do our synthetic division. So 2, bring that down. 2 times 2 gives us 4, 0, 0. Add those up, 0, and remainder. Okay, so we did our synthetic division. And now let's answer all the questions. Quotient, remainder, and EBA. Okay. Let's start with the quotient. What's my quotient here? Jackson, what's my quotient?
2x squared
Yep.
plus 3 over x minus 2. Oh wait, no, just 2x squared.
Yeah, quotient is just 2x squared. If you wanted to write the answer to the problem in polynomial form, that's what you just said, quotient plus remainder over divisor. But they didn't ask for that here, so just your quotient. Okay. How about my remainder? What's my remainder? 3. Yep. And my EBA. Emma, what's my EBA here?
It would be 2x squared plus 3 over x minus 2.
So that would be, again, if you wanted to write the answer in polynomial form, the long division problem, or synthetic division. But here, they're just asking for one specific piece of that, just the EBA.
Would it just be x minus 2?
No, not x minus 2. That's my original denominator. What's my EBA? It's just 2x squared. Yeah. So the EBA is just the quotient. It's not the remainder, it's not the denominator, it's not anything else. It's just the quotient when you do long division. Okay. So 2x squared. Okay, so look at that EBA. If you were to graph 2x squared, is that a horizontal line? What do you think, Nick? No. Is it a vertical line?
No.
No. Is it a line?
No.
No.
It's a curve.
Yeah, it's a curve. So we've never had an asymptote before that curves. Well, this one does. So this is something that we're going to sketch, and we're going to get closer and closer to it. But we're not getting closer and closer to a line. We're going to be getting closer and closer to something that's curving. So it's a little bit more complicated to sketch. Yep.
How'd you get 2x squared for the quotient?
2x squared. So when you do your synthetic division, that's your constant, that's your linear term, and that's your quadratic term. So those are your coefficients. No linear and no constant in this one. But it is possible that you do get numbers here that are not 0, just not in this case. Okay, any questions on that? Now, the reason we don't care about the remainder part, like think about this part right here. Remainder divided by g of x. Okay, let's write that down for our problem. The remainder is 3. And g of x is the original denominator, x minus 2. So 3 over x minus 2 is this part right here. How come as x gets bigger and bigger and bigger, how come I don't really care about this part? 3 over x minus 2. Why do I only care about this part? What's happening to this part as x gets bigger and bigger? Yeah.
It gets smaller.
And what is it approaching?
It's approaching 0.
It's approaching 0. Right? If x is infinity, you're going to have 3 divided by infinity minus 2. Okay? That's an infinitely small number. So adding something that's infinitely small to the quotient doesn't make a difference. Right? Does it make a difference if x is a small number? Of course, yeah. But end behavior means what happens to the graph as x approaches infinity. And this part turns into nothing. Any questions on that? Okay. So that's why we don't really care about this part at the end when you're doing the EBA, because it always turns into nothing, right? Or something infinitely small. All right, so a couple of points before we try to sketch this graph. Okay, there is a difference between the EBM and the EBA. All right. The process to find them is different. EBA is more complicated. Okay, you have to do long division or synthetic. EBM is easier. You just take the highest degree term in the top, divide by the highest degree term in the bottom. Now, when you do each of those, okay, if the question did ask you to find both the EBM and the EBA, they could come out the same or they could come out different. Okay, in this problem, they would come out the same. If you take the highest degree term in the top, it's 2x cubed. If you take the highest degree term in the bottom, it's x. If you divide 2x cubed by x, you get 2x squared. So the EBM and the EBA are the same. So if you're thinking, why don't you just do that instead of long division? Well, the only reason they came out the same this time is because this was a 0 and that was a 0. If those had not both come out to 0, then the EBM and the EBA would have been different. Okay, and the last point, we've already kind of mentioned that, but if you're doing the kinds of problems we did last week, you will always get straight line asymptotes, horizontal or vertical. If you're doing problems where the degree in the numerator is bigger, you can get curved asymptotes. Okay, for that last problem we did on example 5, what was the degree in the top? Oh, Raj, what was the degree in the top? Great, yeah. And Gregory, the degree in the bottom?
2. Negative 2.
Highest exponent in the bottom?
1.
1. Okay, so degree in the top was a 3, degree in the bottom was a 1. What's the difference between the degree in the top and the bottom in that case? It's a difference of, yeah,
2.
it's a difference of 2. The higher the difference, the more complicated it's going to be to sketch. Okay? This one's not bad because it's only a difference of 2. It'd be even simpler if it was only a difference of 1, but it's not, it's a difference of 2. Okay, so I would expect to see something with differences of 1 or 2, where the top is bigger. All right, so now let's use a graphing calculator to graph the original problem. Let's graph 2x squared so we can see what a curved asymptote looks like. Okay, does everybody have what's on the left? All right, let's type that in. When you type it in, how should I type in the numerator? Just to be careful, I need to make sure I do what? Dario, can you tell me how I type that in?
What, just 3?
Yeah, f of x.
In parentheses?
There you go, that's important. In parentheses. Very first thing you need to do.
2x cubed minus 4x squared plus 3 parentheses
Yep, so now you close it.
divided by, and in parentheses x minus 2.
Yep, that's exactly what I was looking for. Okay, so you gotta make sure you put those numerator and denominator in parentheses, because if you don't, it won't come out right. Okay, let's do zoom 6. Probably gonna have to adjust my window a little bit. Now, if you look at the graph, you can kind of see a parabola, like that 2x squared a little bit. So I'm gonna graph that. Let's graph that. You see what it looks like. And if you look at the graph on the left side, you can kind of see that it looks like it's getting closer. Maybe not until I make it a little bigger. But now can you kind of see how the red, which is an asymptote, and the blue are getting closer and closer together on the left side? They should be getting closer and closer together on the right side. If you can't see that, then you are not zoomed out enough. So it's probably off the screen. So let's set the Y max at like 40. And let me just try that. Okay, so what I'm looking for is, can I see the blue one in the upper right? Yeah, now I can. So keep in mind, if your asymptote is a parabola, you should be able to see a parabola on both sides. We couldn't because we weren't zoomed out enough. Now we are. Well, I guess I can't. It's not dragging it over. But it is getting closer and closer to a parabola on each side. What you don't want to focus on is what's happening in the middle right now. Okay? When you're looking at the EBA, you're just looking at what's happening on the edges. And if you block out, I don't know why I can't drag that over, but if you block out the middle, try on your page. There we go. Let's try it again. There. Block out everything that's happening in the middle, and the blue and the red graph are pretty much going to look identical. Go like this, block out the middle, and that's exactly what an EBA and the original function should look like. When you get to the edges or the ends, they should be very, very close. Okay, so that's perfect. We still have to investigate what's happening in the middle. Okay, that's where the vertical asymptote is going to come in, and that's what I'm going to try to show you guys how to do right now. All right, so we did example 6. Just verify that 2x squared looks like the EVA. And now let's try to sketch it. Okay, I went by 2s on the y-axis. I really probably even need to go by like 4s because this graph goes off the screen and it's up pretty high. If you go by 2s, with my graph, I'm only going to get as high as 20. 40 was good. 20, I don't know how much you'll be able to see. Yeah, with 20, you just barely start to get the top of that graph. So I think I'm gonna change my scale and maybe go by 4s instead. Okay, so that'll double the height I can get out of it. All right, so let's update that first. All right, so we got 0, 4, 8, 16, 24, 8, 2, 36. Okay. Oh, I skipped 12, didn't I? It's Tuesday. That's all right. 4, 8, 12, 16, 20. 4, 2. There we go. 4. Okay, so that's going to be a little bit better numbering. X-axis is fine with negative 10 to 10. Go by 1s. All right. So first thing we want to do, let's investigate the vertical asymptote, and then we'll do the EBA, and we'll try to sketch both of them. Okay. What would be my vertical asymptote in this one? Yeah, 2. And how would you write it as an equation? Yep, x equals 2. So let's start with that. This doesn't help you with what the ends of the function are going to look like. It only helps you with what's happening near 2. That's all it does. So we need a vertical asymptote at 2. Okay, so that's a line that we can never cross. So that automatically means my graph is now broken into two pieces. There's going to be something on the left, something on the right. Okay, the EBA. We already know what it is. If we didn't, we'd have to find it right now. Okay, so the EBA is 2x squared. Okay, so let's graph that. And if they do ask you it in an equation form, it's y equals 2x squared. It's what I typed in on the graphing calculator to get the sketch. Okay, so to graph that, we probably want to make a table with a few points. Start with 0. If x is 0, we get 0. How about if x is 2? What would be my y value? Oh, Vanessa?
Oh, geez. 32 squared first, right?
Yeah.
So 4 and then times 2, that's 8.
8. And because it's symmetrical, if you plug in -2 squared is also 4, times 2 is 8. All right. Let's do 3, and then we might be getting kind of to the top of our graph here. If we plug in 3 for x, what would we get for y? Yep.
18.
So 3 squared is 9, times 2 is 18. And -3 is also 18. 4, well, actually we can do 4. We can fit that, but that'll be the last one we can fit. If you plug in 4 for x, what do you get for y? Yep. 32. 4 squared is 16 times 2. And -4 is also 32. So let's graph those points and then sketch your parabola as a dotted line. All right, so we've got 0, 0. We've got 2, 8. Remember, this is not, even though I'm graphing the point 2, 8, I'm never actually going to touch that point because it's on the asymptote. This is just to get the picture of the curve of the parabola. So 2, 8, -2, 8. 3, we're up at 18, so right about there. -3, 18, and 4, we're at 32. So 4, 32, -4. Much better choice to go up to 40 on the y-axis like that. Okay, so now let's sketch that asymptote. All right, so now what we need is some points that are close to the vertical asymptote, and then I'll do some others between -10 and 10, just to get a good idea of the sketch. All right. What would be a good value that's really close to -2, but just to the left of it? Yeah.
Negative 2.0001.
So our asymptote is at +2. So I'm looking for a number a little smaller than 2.
So 1.99.
Yeah, I don't know if I said -2 on accident, but yeah.
You did say that.
Okay, yeah, so 1.999, sorry about that. Okay, we're at -3,000, all right, roughly. So we're going to be way, way down. What would be a value that's just a little bit bigger than 2? Yep. 2.0001, and we're way up at 30,000. Okay, so we know what's happening on each side of the asymptote. And we know that those two blue dots will never connect because they are separated by an asymptote, and you can't cross that. So now I need some more points left and right. So let's do, we're going to do a lot of points. Let's do 1. So 1, -1. Now, be careful when you do this, because remember, we're going by 4s. So 1, -1 is actually right about there, okay? Because my y-axis goes by 4s. Let's do 0. All right, 0, we're at -1.5. So a little bit lower. Let's do -1. Okay, -1, we're up at 1. So just barely above it. And what's going to happen is we're just going to stay very close to that quadratic asymptote. So our graph is going to look something like this. Stay very close. But as it starts to come down, it's going to separate a little bit. And it can't keep following it because it runs into that vertical. So it's going to kind of go through those points. And then it has to go through that point down there. Now on the right side, we need a couple more points. And we're going to end up kind of trapped in between in this little section right there. That's usually what happens. So another good point to check would be like 2.5. I think that'll be one we could fit on the graph. 2.5, we're at 18.5. So 2.5, 18.5, be right about there. And 3 might be one more we could do. 321, yeah, we can do that one. 3 up at 21, so right about there. And 4 might be off the graph, I don't know. No, we can do it, 433.5. 4, 32, oh, right there. So I've got 4 dots in that section in blue that I can connect now. So I'm going to stay really close. Come down, curve, and then stay really close again. And that's exactly the sketch we had. Well, if I set my Y max back at 40, that should look pretty similar to our sketch. Right? So it's like a parabola, but it's broken in the middle. And one end bends up to infinity, and the other end bends down to negative. Okay. Any questions on that? So the key really is sketch your asymptotes first, then plot some more points near the asymptote, and then as many more as you need. Okay? To see that there's a curve in here. You know, if you want more points, you can do more. I would say generally 6 or 7 points is enough. Questions on that? All right. So this one, let's find the vertical asymptotes, the EVA, and we'll sketch it. Okay, because this one's a little different. This is actually easier than the last one. What's the degree in the top this time? Yeah. 2. What's the degree in the bottom? Yeah. 1. That's a difference of how much? It's a difference of 1. So this is going to be an EVA that has a degree 1 for the EVA. The last problem was a degree 2. What does a degree 1 polynomial look like? Yeah?
It's a line.
What kind of line?
Straight one.
All lines are straight. But what kind of line is this one going to be? Yeah?
Linear.
It is linear, yes. All linear, yeah, would mean it's a linear function. But how would that look when you draw it? It's not going to look like the kind of lines we did last week for asymptotes, but it's still going to be a line. What's going to be different about it? Yep.
Diagonal.
It's going to be diagonal, yes. So a diagonal, or what we call a slant asymptote, is kind of in between a horizontal and a quadratic. It's not as simple as a horizontal, but it's definitely not as complicated as a quadratic that curves. It's going to be called a slant asymptote. Okay, so how do we find let's do the vertical asymptote first. Can someone tell me how we find that one? Yeah.
The value of x that makes the denominator 0.
Exactly. Value of x that makes the denominator 0. You can check for common factors, but you don't have any here if you try to factor the numerator. And so what would be your vertical asymptote?
Your vertical asymptote would be 3. X equals 3.
So 3 is the root of the
sorry,
denominator.
X equals 3 would be.
X equals 3 is the proper way to say the asymptote. Yep. X equals, because it's vertical, and then the number. Okay, so there's your vertical. That one's the easy one. Now we need the EBA. What do I have to do to figure out the EBA? Yep.
Synthetic division.
Yep, I'll do the synthetic division. And then what am I looking for after I do that?
The quotient.
I'm looking for the quotient. Perfect. So let's do the synthetic division. So we've got 3, and then we got 1, 4, negative 1. Okay, so let's bring down the 1. 3 times 1 gives me 3. 4 plus 3 is 7. 3 times 7 is 21. And then add that to negative 1, and you get 20. Okay. First thing, just to notice real quick, if I asked you for the EBM and the EBA in this problem, they would not be the same. Okay. Because I didn't get a 0 right there. Okay. Got a 7. But they didn't ask for the EBM, just the EBA. EBA is always written as y equals. And how about, Jade, what's my EBA here?
X cubed.
Let's start, what's my quotient? Let me ask it that way.
Is it 20?
No, 20 is my remainder.
Is it 1 or just X?
That's part of my quotient, it's not the whole thing. The quotient is a binomial in this case. Yep.
X plus 7.
X plus 7. So it's 2 terms because this term wasn't a 0. It is important to write it. So it's 1x plus 7. That's a line with a slope of 1 and a y-intercept of 7. That's going to be an asymptote. Okay, so let's sketch that. Let me, how do I want to do this? Let's get a piece of graph paper. That down there. All right, let's start with the vertical. X equals 3. Okay, can we cross that vertical line? No, never cross a vertical. So you automatically already have 2 pieces to your graph. A piece to the left, a piece to the right. Okay, slant asymptote. Slope is 1, and y-intercept is at 7. Now, a little bit high. You know what? In fact, I'm going to go by 2s then, because I don't think I'm going to get enough graph above 7 to show this. So let's go by 2s. Now vertical asymptote is at 7. And the slope is 1. So I need to go up 1, right 1. So I'm at 7. If I go up 1, I'm at 8, right 1, I'm right there. I know it's a little weird sometimes when you go by a different scale, but just make sure you take your scale into account. Up 1 to 9, right 1. And this is up 1, right 1, even though it looks like I'm only going up a half. So that's enough points. Let's just use the line tool to do the rest of that. About like that, and then I just have to adjust it a little bit. That's pretty good. Okay, so we've got 4 pieces. Basically, if you look at this, it's kind of like an X shape. There's 4 sections. Usually the graph ends up being drawn in 2 of them. So let's first check the behavior to the left and the right of the asymptote. To do that, I'm going to use the table, and I got to type that in. Okay, so be thinking of numbers that are close to the asymptote on each side of it. So let's do x squared plus 4x minus 1. divided by x minus 3. X minus 3. Okay, what would be a good value to check that's very close to the asymptote? Ethan?
Like 2.9.
Okay, so let's check 2.99. Is that to the left or the right of it? To the left. Okay, so we're at a very big negative number. Okay, almost negative 200,000. So we're going to be way, way far down. On the left side. So way down there. So I already have an idea of what section I'm going to be in on the left. I'm going to be somewhere down in here. So I'm going to need some more points to figure out what that looks like. And what would be another good number to check near the asymptote? Nick?
3.00.
Yeah, let's check 3.001. It's not getting a 3. Good. All right, and we're up at almost 2 million. So we're up very, very high. Okay, so just put a dot up there on the upper side. Now that I have that dot, I know that I'm going to be somewhere in this section. What would be another good x value to check to see what's happening in this upper right section? Yeah. Yeah, I think 4 would be a good one. So if we type in 4, we're at 30. Okay, so I didn't even make my y scale high enough. So what I'm going to do then is let's try. Is 3.5 going to be? That's even worse. Let's try 5. All right, 5 I can kind of do. That's not that far off the graph. So 522. So 522. I guess that would be like right about there. And then I think it's going to keep coming down. So 6 might actually be a good point. 620. So then we're right here. But eventually it's going to start to curve back up. So 7, a little bit lower. It's probably about as low as it's going to go. 7 we're at. Actually, I should have put it just a little lower. 719. And then let's go to 10, which is the edge of my graph. Okay, so 10, now it is going back up again. So I'm at just about 20. All right, so what's going to happen in that section is it's going to, imagine that part continues. It's going to curve, stay right up against that. But in this section, it's going to kind of come down, curve, and as you continue to the right, it's going to keep getting closer and closer to that green slanted line. Now, we got a lot more room down in here, so we should be okay. What's a good x value to check in the lower left section? Yep.
2.999.
Okay, so we've already checked that one. We know at 2.99 we're going to be way down at negative infinity. So we've got that done. So we need a few more that are further away now from the asymptote. But that is a good one to check. We just already did. Oh, Marcelo? 2. Yeah, I think 2 is going to be a good one. We should have enough room. 2, negative 11. So 2, we're right here, and then negative 11. 2, 4, 6, 8, 10, 11. Good. Another good one would probably be 0. 0, almost the origin. 0, negative 1/3. Or I'm sorry, 0, positive 1/3. It's right about there. So I can kind of see the curve a little bit. And then let's just get one more point, like over in that section. What would be one more good x value to check? Oh, Vanessa? Sure, let's do negative 3. And that's 2/3. So negative 3 at 2/3. So it's actually still going up in that section. but that's probably pretty close to where it's going to max out, because now it does have to start coming back down. Let's do -10. And now we're at -4.5. So -10, 1, 2, 3. Oh, it's going by 2, that's right. So 2, 4, that's probably about -4.5 around there. So we can see it is starting to get closer to that asymptote again. So keep it pretty close. It's starting to curve away, curve down, and get closer and closer. That's a pretty typical sketch when you have a slant asymptote, those two curved sections. All right, let's take a look. I'm going to set my window, I'm going to keep it at 40, because if I set it to 20, the only thing you're going to see on the calculator is a very tiny little section like that. You wouldn't see much. So let's set it at 40 and keep everything else the same. Okay, so there's the part in the lower left. And there's the part that's supposed to be in the upper right. That's pretty much what ours looks like. And it just barely goes above the x-axis for a little bit in this section right here. Okay, so another thing I could ask you to find now would be the x-intercepts. As long as you get the graph, you could use the calculator to figure that out. Or you could set the numerator equal to 0 and use the quadratic formula, and that would also give you the x-intercepts. So remember, setting the denominator equals to 0 gives you your vertical asymptotes. Setting the numerator equal to 0, that's getting your x-intercepts. All right, any questions on that one? I'm going to do another sketch, but let's just find the EDA here and the vertical asymptotes. So we'll find what we would need to do a sketch, but we're not going to sketch it. Okay, so first thing, what kind of EDA is this going to have? Will the degree be a degree 1 or a degree 2? Yeah. Right, it'll be a degree 1 because the numerator has a degree 3, the bottom is a degree 2. That's a difference of 1. So that would be a slant asymptote in this problem. To find this asymptote, I need to do division. Can I do synthetic division? No, can't do synthetic division this time because it's not a linear polynomial on the bottom. So you have to do long division. So that's why I want to do this one, because we haven't done anything with long division today. Okay, and I've already mentioned this to you. This is going to be a slant asymptote. I'm going to move the graph off because we don't need it. Okay, so on the outside we've got x squared plus 2x minus 3. And Annalise, how would I set up the inside?
Put the 2x cubed plus the 7x squared minus 4.
Careful.
0.
Plus 0x, yep. So we need a placeholder because we don't have any 0. We don't have any linear terms. Okay, and then minus 4. All right, so when we divide, first thing we do, 2x cubed divided by x squared, that's going to give me 2x. Multiply it back out. 2x cubed, 4x squared, minus 6x. And what do I do with these columns that I just created? Subtract. 2x cubed minus 2x cubed is gone. Travis, 7x squared minus 4x squared. Can you finish off the last column for me as well?
6x.
Perfect.
6x.
Plus 6x. Now, technically, we don't even need the plus 6x or the minus 4 because we are not interested in the remainder. We only need the quotient. And the quotient, all I'm going to do now is 3x squared divided by x squared, and I get plus 3. There's my EDA. 2x plus 3. If you wanted the remainder, then you'd have to distribute the 3 back out and finish that off. Okay. But it doesn't ask for the remainder, so we're not going to do it. Okay, so EDA, properly written, y equals 2x plus 3. So there's my EDA. And vertical asymptotes, we need to try to factor the denominator, x squared plus 2x minus 3. How would the denominator factor? Yep.
It would be x plus 3x minus 1.
Yep. X plus 3, x minus 1. Let's check it. X squared minus x plus 3 is plus 2. Yep, looks perfect. So now we have 2 vertical asymptotes. -3, +1. Did I say positive? -3, +1. And we're not going to sketch that. But any questions on how I found the asymptotes? Okay. And again, that is called a slant asymptote. So the only kind of non-linear asymptote we looked at today was quadratic. We did look at another type of linear, that's slant, but the EBA can be higher than quadratic too. If the degree in the top was a 5 and the degree in the bottom was a 2, that's a difference of 3. You could have a cubic asymptote. Okay, but we're going to mainly focus on quadratic and slant. All right, and this one, they're asking us to use a calculator. So the reason we're going to use the calculator is because there's some hidden behavior that we need to check for. And I just want to see if we can find it. Okay, first thing, what would be the degree on your EDA if you were going to find that? Yep, degree 1. This has a slant asymptote. So when we sketch this, I definitely want to be able to see a slant asymptote as part of a good picture. So let's type it in. Put in 2x to the 4th plus 7x cubed plus 7x squared plus 2x. And we divide by x cubed minus x plus 50. Okay, I'm going to start with zoom 6, make sure, I'll see how that window looks, and then we'll go from there. Okay, so let's start with that. Does that look like a complete window, complete graph? No, I can't see the slant here. All right, I'm thinking that maybe the slant looks something like that, but that doesn't look like what the upper right is doing at all, unless the upper right starts to curve back down at some point and then level off to that. So I definitely want to set my Ymax, and I'd like to see more down in the lower left. So I'm going to set the Ymax higher, and I'm going to set the X-min and the Y-min lower. Okay, so let's see if we can get a better window. Let's set the Ymax up to, let's try like 35. Let's try the X-min at -25. And let's do the same for the Y-min. So my goal is to see a little bit more in the lower left and more in the upper right. All right, well, I definitely can see more in the lower left, and it really looks like it's a slant asymptote. Okay, now I'm starting to see a little bit better in the upper right. It is curving back down and starting to level off. So I'm going to set the X max a little bit higher, and then I think that'll be a good window that shows you a big picture of what's happening. But the big picture is not the whole story in this one. And I can now see it curving back down in the upper right. It's perfect. That's a pretty good big picture view. If you put in your asymptote, it probably looks about like that. Getting closer and closer on the lower left and the upper right. Okay, so that's a good big picture. But what else is happening in this graph that we might need to check out a little bit closer? Something here we need to check out a lot closer. Yeah?
The x-intercept.
The x-intercepts, if there are any. I need to zoom in on this section right here. I can't tell at all what's happening there. I mean, when I had the zoomed in view, I don't know, it looked pretty flat to me. So let's go back to zoom 6. Okay, but you definitely need the picture we just had to show you the overall view. But now I'm going to start to zoom back in. And let's zoom 6, that's not even enough. We need to go a lot more. To zoom in on that section, I need to adjust my Y min and max. What would be a good value for my Y min and max if I want to zoom in on that part that looks pretty flat? Yeah.
Maybe 5.
5 for the Y max up here. And then what about the Y min?
-5.
Okay, so -5 to 5 would give you an area about like that. Could we zoom in even tighter? Does it look like we have to go all the way up to 5? No. What would be like an even tighter window we could zoom in? 2? All right, we could do 2. I think we could go even tighter, but we could start with -2 to 2. That's going to really start to zoom in on the x-axis. So from -10 to 10, we just zoomed in like 5 times as much. But it's still kind of hard to see it. So what would be another good value I could set for my Y min and max? Yeah?
Oh, 1 and -1.
Okay, we're still pretty far away from that though. I mean, that would get you to right in there. But let's go even tighter. Yeah?
0.1 and -0.1.
Yeah, let's do 0.1 and -0.1. Okay, let's really start to zoom in. So -0.1, 0.1. And I also don't need to go beyond 2 and -2 for the x's. All the interesting stuff is happening right in there. So I would say, even if you want to do like -3 to 2, that's plenty of room on the x-axis. So we've completely lost the big picture now. But that's important because we have to see what's happening on the x-axis. And what started out looking pretty flat originally is not flat at all. And that was the important thing I wanted you to see here. Okay, so we started with that picture, and then we zoomed in again to that picture. And how many times does it look like this graph crosses the x-axis? Yeah.
4 times.
Yeah, it does. It crosses it 4 times. You might have to zoom in a little bit more to see it, but I think you can see it pretty good. that's something you couldn't see at all in this view. So the point is, when you see a question, if something looks very flat, or if you know it's supposed to have a certain kind of asymptote and you're not seeing that, you might have to zoom out a little bit more to see the big picture, or you might have to zoom in more to see the detail. You need both windows here. Any questions on that? All right, so that's the last part of 4.2. So let me see. Okay, so you guys are just doing the top one. So it's 40, 41, 45 to 47, 51, and 55. Not a ton of questions because there are some graphs that take a little bit of time, and it was only half of a section. Okay, so you've got just under 15 minutes left. So you can use the time to start that, ask me any questions, or if you want to see how you did on your tests or check the questions, I can show you what you got right now.